Welcome. Let's take a look at number 2, and it says, consider this game where we have a spinner with 4 regions of equal size, and after spinning, you'll win the amount shown in the region on which your spinner lands, and the game is free to play, and we'll let X represent, so our random variable X will be the amount you win on a spin. All right, so X is a random variable because I don't know what X will be until you actually do the experiment, spin the wheel. All right, so even though I don't know what you'll win if you spin, I do know what you could win. So I'm going to list all possible values of X. And I'm even going to include units in my table here. So for emphasis, you might win $0, or you might win $4, or you might win $100. And then to turn this into a probability distribution. So in a probability distribution, we not only list X, but the corresponding probability for each of those values of X. All right, so out of the 4 regions, 2 of the 4, you're going to win $0. So $0 has a 2 in 4 chance of occurring. And then the $4 region, just 1 region out of 4, $100 region, 1 out of 4. And then we'll check the condition here that to be a probability distribution, if we add our probabilities, we have to get 1 or equivalently 100%. So let's add our probabilities, 2 out of 4 plus 1 out of 4 plus 1 out of 4. And we have our common denominator 4. And adding the numerators, that is also 4. So we're good there. We do get a total of 1 for the sum of the probabilities. Okay, so that's called a probability distribution for this discrete random variable X. And then we take this one step further. So it says, well, we can't predict the result of one spin. So you spin once, and I don't know what you'll land on until you actually spin. But we can predict your long run average, meaning if you played the game a large number of times, we can figure out what you're averaging out to per spin. And this is called the expected value of X. So the expected value of the random variable is what it averages out to in terms of money per spin if you spin this wheel a large number of times. All right, so let's see what that looks like in action here. So here's our formula. So E, capital E for expected value of X, so function notation, E of X, expected value of X. And it's also called the long run average or the mean of the random variable. So it will be the population mean of the random variable X. Okay. So it's actually just a weighted mean where the weights will be the probabilities. So the formula will be capital sigma, we'll be adding each value that is the product of X times its weight, which is its probability. All right. So I'm going to put my numbers in parentheses when I'm looking at the pairs, the X and its P of X. And I'm even going to include units in the math for emphasis here. So $0, its probability is 2 out of 4, plus $4 for X, its probability was 1 out of 4, plus $100 for X, and its probability is 1 out of 4. Okay, so I wanted to leave everything in fraction form here, and we have our common denominator 4. So in our numerators, so you can kind of think of this as sort of in theory that since each of these regions is equally likely, let's just think of landing then on the $0 region twice. So 2 times out of the 4. and 0 times $2 would be nothing. So for those two regions, you would win nothing. Plus, and then $4 would happen once, plus $100 times 1 is $100. All right, so in theory, the denominator there, if you spun 4 times, you would make 0 plus 4 plus 100 is $104. All right. But we want to know how much that is per spin. So dividing by 4 is what's happening there. So if you had $104 and you got that by spinning 4 times, when we divide by 4, you're averaging out $26 per spin. So if you were to play the game a large number of times, so this game, not once, not twice, but over and over, a large number of times, you would be averaging out to $26 per spin. Okay, so the reason for showing you the two spinners here, if you add up all the dollar amounts on this spinner, it's 104. If you add up these 4 values, it's still 104. So the key here is that if you only play the game once, these are very different games. So I don't know which one you would prefer to play if I said you could only play once. So you can think about what your answer to that would be. Would you prefer to play this game once and risk getting nothing, but possibly gain $100? Or would you rather spin this spinner once and just be guaranteed $26? So very different if you play once. But if you played over and over and over again, you can just think of like, I don't know, a really big number, like play it 1,000 times, each one 1,000 times. This one will balance out to that same result if you had spun that spinner. So that's the idea of what we call the law of large numbers. So if we repeat the experiment over and over a large number of times, we can predict what will happen. All right, so that will lead us into just a few more problems here with expected value. And I just repeated here then, the expected value of a random variable, often referred to as the long run population average. So again, if we do perform an experiment over and over again, it's what we would expect the average value of the variable to be. So in this section, we are going to focus on the formula we just discussed, the mean or expected value of the discrete random variable. However, I did include, just for reference, the formulas for population variance, as well as population standard deviation and their symbols. So in this section, we're not actually going to calculate variance or standard deviation, but we will coming up in another section. And it's also good just to remind you of symbols. All right, but we'll move forward here to another example, a business example. And again, just repeating that idea of the law of large numbers. So let's just jump in here with our company here that makes electronic gadgets. And 1 out of every 50 gadgets is faulty, but the company doesn't know which ones until a buyer complains. All right, so the manufacturing process isn't perfect. They do know that occasionally 1 out of 50 times they will send a customer a bad gadget, and the other 49 times out of 50 then the gadget would be good. So what they also know is that they'll make a $3 profit when they sell a working gadget, but it's going to cost them, they'll suffer a loss of $80 for every faulty gadget because they have to repair the unit. All right, so very simplified model here of a business example, and we'll kind of check out what the company can expect if they sell a lot of these gadgets. So it says, can the company expect a profit in the long term? So if they sell many gadgets, we're going to calculate the long-term average of the random variable X So X is their profit on the sale of a gadget. So let's start with our table here and keep track of what could happen with their gadgets. All right, so the gadgets that they're producing will either be working or they will be faulty. So an outcome could be a working gadget is sent to a customer, or a faulty gadget is sent to the customer. All right, so let's talk profit here, X first. All right, so if they send out a working gadget, they're making $3 on that. And I'm again going to include units for emphasis here. So they'll make $3 on every working gadget that they sell. And then they're going to suffer a loss of $80 if it's a faulty gadget. So a profit, then a loss would be negative profit. So negative $80. And again, I'm just putting units for emphasis there. Okay, so let's talk probability then. All right, so 1 out of every 50 is faulty. So I'm going to do the faulty probability first. So 1 gadget out of every 50, which means that how many gadgets out of every 50, how many are working? Well, if 1 is bad, the other 49 would be good. So this is our rule of complements. The 1 is the bad one, the remaining would be good. So if we add our probabilities again, we would definitely get 1. So 49 plus 1 would be all 50 of them out of the 50. Okay, so let's see if the company can make a profit on these gadgets if they sell a lot of them. So just a reminder here, let's say they only sold 1 gadget. If they only sold 1 gadget, they're either going to make $3 or they're going to lose $80. What we'd like to know is, what if they sell lots of gadgets? Will their profits, their gains, outweigh their losses? Because it looks like there's a pretty big loss here compared to their profit when they send out a bad gadget. All right, so let's see what we find out here. So the expected value of X, again, it's called the population mean for that random variable. So we're looking at adding each X times its probability. And I just put them in parentheses for emphasis here. And again, I'm going to include units. So the first X was $3. So its probability, 49 out of 50. All right, so think of this sort of in theory. Out of 50, if they sold 50, they're going to make $3 49 times. So that's the XP of X there, plus they're going to lose $80. Its probability, 1 out of 50. All right, so in theory, out of 50 sold, they'd be losing $80 just once. So let's look at numerators here. So I have my common denominator, 50. So the numerator is 3 times $49. So in theory, out of the 50, they'll be making a total of $147 based on 49 of their gadgets being good. All right, and then plus, and plus a negative. So I'm going to write subtract there, minus. All right, so now they are going to lose $80, but it just happens once. So that's going to be minus $80. So hopefully what you can see here is that their gain here is outweighing their losses because they're selling so many good ones. Even though it's only a $3 profit, they're selling so many good ones that they're able to sort of deal with that loss and still come out ahead. So let's look at that numerator. So 147 minus 80, they're going to be up $67 total. But what is that per gadget? So if we divide by the 50 gadgets, so now divide that by 50, and they're making $1.34 on average per gadget. So on average, they can expect to profit $1.34 per gadget. This is assuming they sell a large number of gadgets. So again, if they only sold one and it was good, they'd make $3. Right? But in the long run, eventually, you're going to see these probabilities kick in where 1 out of 50 is a bad gadget and the other 49 out of 50 are good, balancing out to still a profit. All right, so that is the concept of expected value of a discrete random variable. And we'll take a look at some more examples.